The big questions that I ask is, how does the order of play affect equilibrium outcome in games? This paper takes the first step in answering that question. I take a specific game, a public good game, which is a metaphor for social cooperation and solving collective action problems, and see how outcome changes with the order of play. Knowing this, we can set rules and regulation on timing and information to shape the outcome accordingly. Here's a summary of my results. The setting is a public good game where cohorts of identical agents play sequentially. The first result that I have is that the equilibrium exhibit a cutoff behavior. All players before the cutoff don't contribute, and all players after contribute. The second result, the equilibrium contribution, which is the total public good provided by the players, is invariant under contributing cohorts. So you can permute the cohort and still have the same total level of public good. Third, having less contributors may increase overall contributions. Fourth, with fixed cohort sizes, the most efficient structure, the structure with the most public good raised, would be the one with increasing cohort size, so more players play later. This work is related to several strands of literature. Obviously, the sequential public good games, Varian 1994, and more recently, Gallis and Monson in 2019. Also, it's related very closely to the timing of player literature. Vinosar 2021 is a paper that's most closely similar to mine. In that paper, he considers a similar timing structure, similar kind of question, but the analysis is on a game of contest. So it asks the question of how should you structure play in order to get the most effort from the players. The model is a game of contribution. N players, each have a strategy space 0 to infinity. They can contribute 0 or positive number. The payoff is identical to all players, and it's given by the formula in blue, the payoff function in blue. If you give more, it hurts your payoff, but it raises the level of public good. And the parameter alpha is the preference for public good. The higher the alpha, the more the agents like public good. There are T periods in the game. Each player I is specified to play in period Ti. So the vector T that lists the time of play of each player is called the order of play. That's when each player gets to play. But players are identical, so you can split up the N players into NT, into the union of NT, where NT is a set of players at time T. So all the sequential order of play information can be captured by the sequential structure vector N. N1 is the number of players that plays at time 1. N2 is the number of players that play at time 2, and so on to NT. This is all the information we need to analyze the outcome of the game. So as an example, this sequential structure is 2, 4, 1. 2 players play at time 1, 4 players at time 2, and 1 player at time 3. The goal of the paper is to find the equilibrium outcome of the game for each sequential structure N. If it's a simultaneous game, then it's N and all zeros. If it's a hierarchical structure, then 1 player play at a time. The N vector, the sequential structure is 1, 1, 1, 1. The object of interest will be the aggregate outcome, the sum of the contributions of all the players for each sequential structure. First, the equilibrium characterization. I found that it exhibits a cutoff behavior, the time T bar, which depends on the sequential structure and also on how much the agents like the public good. If agents like the public good, the cutoff will be earlier. If agents don't really like the public good, then the cutoff will be later. All agents before the cutoff don't contribute, and all agents after the cutoff contribute. For example, if the preference for public good alpha is between 0 and 1, in this case, in this example, only the last cohort will contribute, the player 7. If alpha were to be higher, 1 to 5, between 1 and 5, then the last 2 cohort contributes, the cutoff is time 2. If alpha were to be yet again higher than 5 in this case, then all the players in the game will contribute because the cutoff is at time 1. Equilibrium can be characterized completely given by this formula, and this relates to the games on network literature where the G here works as similar to the adjacency matrix in the games on network. G here is defined by that you connect to someone if that other player play at the same time or earlier than you. Let's move on to some implication. So the payoff decreases as you play later, which means that if you allow the players, if you endogenize the time of play, allow the player to announce when they want to play and then play the game, then everyone would want to play as early as possible. This means that the outcome of the extended game of observable delay is the outcome of the simultaneous move public good game. The equilibrium level, the contribution level, depends on the preference for public good alpha, and it's given by this closed form formula. It is increasing and strictly concave, but it is piecewise. It has kinks around where alpha equals to some function of the number of players. About efficiency, the more sequential the structure is, the more inefficient it is. So the least efficient structure is the hierarchical structure where one player play at a time. The most efficient is the structure where it's a simultaneous move game. But yet again, it's not as efficient as the optimal solution, as is well known. We can order 2 sequential structure by how far or how close, rather, it is to the hierarchical structure. I define sequentiality of the structure N to be how close it is to the hierarchical structure. The closer it is to the hierarchical structure, the less efficient it is, the more inefficient it is. One other implication is sequential neutrality. So given 2 sequential structures, if you reshuffle or permute the cohort, then under some condition, the level of public good will be the same. So in this example that I have, 10, 1, 10, so 10 player, 1 player, and then 10 player, and N prime, 10, 10, 1, it can give the same amount of contribution if alpha is sufficiently high, so agents like public good. Other implication is that removing a contributing player may result in higher equilibrium of public good. So you have to be careful when you're choosing which area to do fundraising, because less populous area might be more profitable. The last application is sequential fundraising. Consider 2 locations, NA and NB. A has more players. Should you do fundraising at A first or B first? The answer is that you should do fundraising first at the less populous place and move on to the more populous place. This result extends to more than 2 locations. So if there are K locations, you can rank them by how many players that there are at each location and do the fundraising from the least populous then to the most populous. So in conclusion, I explore how equilibrium changes as a function of how sequentiality the play is. And there are many interesting questions that I can ask. I can do the same analysis for many other games and see whether I can say something general about equilibrium and the structure of the game tree. Thank you.